Last year, astronomers watched a star swallow a planet alive. It really happened, and we caught the flash in real time. Stars do eat planets when orbits decay or the star swells. Today, we will see how that feast actually works. Gravity and drag steal energy from a planet's path, causing a plunge, or the star expands and the atmosphere becomes a lethal net. Either way, the star wins, and the planet dissolves into fire. That is not rare for stars like our Sun. We even see chemical fingerprints left by digested worlds inside starlight. Let's unpack the scenes that turn worlds into fuel. Picture a star like the Sun, aging and running out of hydrogen. As the core contracts, the outer layers puff into a red giant. The surface cools, but the radius balloons beyond the inner planets. Gravity at the swollen surface grows weak, while frictional gas thickens. A close planet now plows through that extended atmosphere each orbit. Every pass drags on it, bleeding orbital energy as heat. The orbit shrinks and the next lap dives even deeper. Deeper means denser gas, so the drag grows brutally strong. A runaway begins, a spiral that tightens in months to years. Inside the envelope, the planet heats, ablates, and sheds its mass. Hydrogen and metals strip off, feeding fresh fuel to the star. That inflow releases light, and sometimes a short infrared glow. The star can spin up slightly from the planet's stolen momentum. Elements like lithium spike at the surface, briefly defying normal depletion. Those chemical oddities are like crumbs on a cosmic tablecloth. A giant may swallow several worlds, leaving layered signatures in time. Mercury and Venus face that script when our Sun swells. Earth's fate is closer, and it depends on competing effects. Mass loss lifts orbits outward, yet tides and drag pull inward. The contest decides whether rock bakes outside or melts inside. Not every meal waits for old age. Young systems are messy, with gas disks and migrating giants. A Jupiter can form far out, then drift inward through the disk. Spiral waves push on it, and momentum trades like bumper cars. Sometimes it stops uncomfortably close, becoming a hot Jupiter. Temperatures hit 2,000 Kelvin, and atmospheres stream like comets. Stellar tides then keep stealing energy, a little each orbit. The orbit decays slowly, but the end is baked in. Magnetic interactions add friction, stirring charged winds between star and planet. If the star is active, the decay can accelerate noticeably. Over millions of years, the safe distance becomes a trap. Once inside a critical threshold, tides outrun the planet's resistance. The world starts losing altitude faster than it can circularize. At closest approach, the dayside glows white and metals vaporize. Some mass escapes as a tail, feeding the star ahead. That escaped gas also increases drag, making the spiral steeper. Think of a snowball rolling downhill, gathering more snow. The final plunge can happen abruptly, after a long, quiet slide. A tiny dot skims a rolling stellar surface, leaving a bright wake. Silence in space, but the physics is screaming. Then, the dot vanishes. Here is the engine underneath the drama in plain terms. Tides raise bulges on both star and planet. If the bulge lags, it tugs backward, draining orbital energy. Friction inside the star converts that energy into heat. The planet also feels internal friction, which saps its spin. When atmospheres touch, gas drag becomes the dominant brake. Drag is proportional to density, velocity squared, and cross-section. As the planet dips deeper, all three factors usually rise. That is why the decay often runs away near the end. Cross too close, and the Roche limit, a tidal boundary, tears the planet apart. Gravity cannot hold the far side, so material peels off. The fragments spread into a stream, then smear into a torus. That ring spirals inward, feeding the star over weeks to years. Angular momentum still matters, so the star can spin up. Observers sometimes measure faster rotation, matching a recent gulp. These linked processes build the script that ends a world. We are not guessing here because the sky has receipts. In 2023, telescopes caught a star brightening as it swallowed a planet. The object sits about 12,000 light-years away, within our galaxy. Optical light flared, while infrared light rose and lingered from dust. That dust likely formed from the shredded planet, warmed by the star. The event's nickname is ZTF SLRN 2020, a mouthful with a clear bite. Before that, clues stacked up from hot Jupiters on doomed paths. WASP 12 billion, with a 1.1-day orbit, is spiraling inward. Its transit times drift earlier, matching tidal decay predictions. Spectra show metals and escaping gas streaming from the dayside. Some sun-like stars show odd enrichment, especially in lithium and iron. Lithium normally burns away, yet it can spike after a gulp. We also see stars spinning faster than peers of the same age. A recent meal can deliver that extra angular momentum. White dwarfs add a separate, brutal line of evidence. Their atmospheres should be pure hydrogen or helium, yet metals appear. Those heavy elements sink quickly, so they must be constantly supplied. Debris disks and falling asteroids fit the bill, raining wreckage down. Taken together, the pattern screams one thing: stars really do eat planets, and we can watch the crumbs. After a sun-like star sheds its envelope, a white dwarf remains. It is Earth-sized, yet half the sun's mass, with crushing gravity. Any close planetesimal that wanders near is torn apart. Tidal forces shred it into gravel, dust, and vapor. The pieces spread into a flat disk, glowing in infrared. Gas from the disk then spirals down magnetic funnels. Metals land on the surface, tattooing the spectrum with lines. We can measure calcium, iron, magnesium, and silicon in detail. Those ratios look like the guts of rocky worlds. Sometimes, we even see water signals, hinting at icy bodies. Because heavy atoms sink in days to years, the supply continues. That makes white dwarfs cosmic autopsies of former planetary systems. Each polluted atmosphere is a case file from a destroyed world. From these files, we learned that rocky planets formed widely. We also learned that gravitational pinball continues long after starlight fades. Planetary meals do not end with red giants. A ring of dust circles a tiny white ember in darkness. Nothing moves fast, yet everything is falling. The silence feels heavy. Gravity does the talking. All right, what about us and our long-term odds? The sun will exhaust core hydrogen in about 5 billion years. The core will contract and the envelope will swell enormously. Mercury is almost certainly gone, with Venus very likely next. Earth sits near a knife edge between escape and engulfment. As the sun loses mass, our orbit expands to safer distances. At the same time, tides and drag will try to pull Earth inward. Which effect wins depends on details of the sun's bloated atmosphere. Some models say Earth grazes the envelope, then spirals down. Others keep Earth outside, roasted but intact, under a blood-red sun. Either way, habitability ends long before the giant phase begins. The brightening sun will boil oceans in under 1 billion years. Plate tectonics may stall while air escapes to space. Any life would need engineering, shade, or interplanetary moving plans. If Earth is swallowed, it adds a last spark of light. The sun might spin a touch faster, then settle into ashes. If Earth survives, it orbits a white dwarf under cold skies. The moon's orbit would widen and tides would weaken. In every version, our neighborhood changes beyond recognition. That first line promised a star eating a planet, and it delivered. We watched a world vanish and learned the playbook behind it. Gravity, tides, and gas turn orbits into dinner. Our sun will follow the same laws on a different clock. Tap subscribe and bring your curiosity back next time.